All right, so in the last lecture, I gave you a brief sketch of how to apply Nash's iteration to the Euler equation. And as mentioned in the last lecture, today I'm gonna show you the error estimate, at least at the heuristic level. And along the way, you can see how the perturbation that we added at Q plus 1 step looks like. And also you can see how to achieve the Holder regularity of the solution. Okay, so let me start. So we are at this section of Nash iteration. Okay. And let me first start with the construction of the perturbation. W. So this denotes the Q plus 1 U. Okay. Okay, so as mentioned last time, we're gonna construct this correction in a way to solve low frequency part equation. And before that, let me first start with the ansatz. So I'm gonna consider the perturbation, which essentially looks like this: some low frequency part function and some high frequency part function. So this low frequency part function will be decided when you solve the low frequency part equation. And this high frequency part function will be chosen to make this new correction to have high frequency, like lambda Q plus 1. Okay? Then the most natural choice for this building block, so we also call this as a building block flow. The natural choice for this would be perhaps something like this, which is given as a plane waves. Because when you use, for example, cosine, you know exactly what the frequency support is, right? And here, k is just a vector for the direction. So let's say this k and k perp is the orthogonal vector. So both k and let's say k perp has the unit length, and k perp is some vector which is orthogonal to k. And the reason why I introduced this orthogonal vector is that so eventually we need to make this perturbation divergence free. And this way we can, at least at the level of building block flow, we have divergence free condition. So this is divergence free. Okay. And well, since it only has a one direction, let's actually take summation over k. So we'll choose the finite number of vector k, vector direction k, and then take summation. Okay. And now let's recall the low frequency part equation. For W, which looks like this, minus RQ, the same with we actually need to solve this equation just inside of the divergence. Okay, and now you simply plug our ansatz to here. Then what you're gonna get is the following. You have summation in k, and let's say k prime. And we have a k prime, and there will be also building block. And now if you look at this tensor product between building block flows, when k is not equal to k prime, we'll have interaction between the cosine in a different direction, so which will only generate high frequency terms. But when k is equal to k prime, you will have cosine square, right? And since, well, you know, as if you do simple computation, this one will generate low frequency term and high frequency term. And since we only care about low frequency parts, this part will be also gone when you take the projection operator. So what you're gonna get is summation over k, a k square, and this is actually the average of the cosine square. Dx and k tensor. Okay. So again, when k is different from k prime, we only get the high frequency part. So when you take the projection operator, it will be gone. And when k is same with k prime, it generates both low and high frequency term. And again, if you take the frequency projection operator, this term will be gone. And only term that we have is the mean of this term, which is here. Okay. So now our low frequency part equation is reduced to the following simple algebraic equation. And I won't go into how to solve this equation, but let me briefly sketch. So if you use something, okay, so first you can sort of assume that minus RQ is a positive symmetric matrix. In the following sense. So we already know RQ is a symmetric matrix. And now if it's not positive, then you can just simply add some identity matrix, which let's say the size is 2 times of the zero norm of RQ times IT, the identity matrix. This term will disappear when you take the divergence. So you can simply add this term to make this one positive symmetric. So in some sense, you can assume this. And the geometric lemma, I think Camilo will cover more detail. Tells us that any positive symmetric matrix can be written as a summation of rank 1 tensors with a positive smooth coefficient. So by matching these two representations, you can actually determine the coefficient. So yeah, so these AK are at the frequency of lambda q. Yes. So if you put this high frequency term, then this will become high frequency. But as long as this building block flow stay very low frequency, their multiplication will remain as the low frequency. Any other question? Okay, so by geometric lemma, okay, you can solve this. This one I wanted to say. This is and if you choose the mean of this building block flow to be k tensor k, so in our case, you probably just need to multiply by square root 2 here. Then you can expect that the size of a k square, is same with RQ. So the size of coefficient is essentially the square root of the size of RQ.
If I remember correctly, yesterday you talked about the space, so you are looking for solution based on intersection link ET minus.
So here
so
I'm on.
How do you measure that RQ zero?
RQ.
It will not be infinite.
Yeah, so you measure actually in the different norm. Because there the question is, like first you want to see how much differentiability parameter we can get in S3 norm. So actually you measure L3 norm. But I mean, this relation is anyway correct.
Yeah, my question was how to make it positive.
Okay, so you just need to, okay, what you need to add is this, so the absolute value of this, right? And then this one disappear in the divergence, but this will generate pressure. And you can just adjust the pressure increment to have this. Yes. Yeah, but at this moment, since we are talking in the Holder space side, so we have a control of C0 norm, so it's easier case. But yeah, that's a good point. Okay, any other question? If not, okay, now let me move on to the error estimate. And in this lecture, I will only consider at the heuristic. Okay, first recall the equation for W, the correction. Then it looks like this. And as mentioned in the last time, so since W is designed to cancel out the low frequency part, so the low frequency part of this one is designed to cancel out RQ. So this one actually have only high frequency term. And well, pressure will just choose this one is equal to 0, so you don't need to worry about this. And the idea behind in this computation is that we want to make this RQ plus 1 small by using this high frequency, these first line terms are all have frequency localized at large number lambda q. Okay. Okay, but before we measure the size of RQ plus 1, we need the inductive bound. So let me first introduce this. Okay. So first, let me introduce parameters. RQ, as I mentioned earlier, is given as a double exponential function. So let's say lambda to the power b to the q, where lambda will be some very large number, and b, as you will see, will be some number which is greater than 1 but very close to 1, and q is just index. Okay. And let me introduce another parameter, which is denoted by delta q. And it is defined as lambda q to the power of minus 2 beta. So this parameter corresponds to the size of the stress error, RQ. And here, this beta will be related to our the Holder exponent of our the eventual solution. Okay. And then now let me give a size of the bound of RQ. And as mentioned earlier, so the size of RQ will be denoted by delta Q plus 1. And then since the RQ has a frequency localization at lambda Q, when you take the spatial derivative, then you will get the nth power of the lambda Q, quite natural. And we also need to propagate the material derivative estimate. So here, this dtq denotes the time derivative plus uq in a product. Okay, so the direction derivative. And okay, and the cost corresponds to the Lipschitz norm of velocity. And this part may not be that obvious at this moment, but you will see why throughout the lecture. Okay, And then once you have this, now you can also introduce the estimate for UQ. And recall that this velocity consists of all the corrections added up to Q steps. So the summation up to Q. Okay. And if you use analogy, you probably expect that this Q prime, WQ prime has the size, has the following shape: RQ minus 1 raised to the power 1/2 in terms of size, and then there will be some building block. But again, this building block flow will be, looks like cosine sine. And now if you measure this one in C0 norm, then this will be controlled by the size of RQ minus 1, C0 norm raised to the power 1/2. So which will be the size delta Q raised to the power 1. Okay. So based on this motivation, one can introduce the inductive bound for the velocity in the following way. So for UQ, since this number decreasing as Q goes to infinity, one can simply put the following way. On the other hand, once you have derivatives for n greater than 1, then the gradient of, so the nth derivative of WQ will dominate, and their size is essentially lambda Q to the power n and delta Q 1/2. Yes? Upper bound, there's no upper bound for B. Yeah, B will be, you'll choose B close to 1 to achieve the better Holder regularity. That will be, you will see in the heuristic. Okay, and here, I will just, for simplicity, I will just propagate infinite number of derivatives. So here, the range of m and n is just any positive number, and here n is any number greater than 1. But in practice, you will actually propagate finite number of derivatives and use some modification technique to have estimate for infinitely many. But I won't go into this technical part. Okay. It's written a bit messy, but this is the inductive bound for RQ, and these are inductive bound for UQ.
Everything is C0, right?
Yes. Here, C0 no means that the space-time. Okay, so now, so now what I want to do is the following. What I want to show is the new error has the size delta Q plus 2. Because if you look at the inductive bound, that's what we need to show. And if you also think about how we design this inductive bound, the size of RQ is the most important. So I will just focus on this part. And now, as we discussed before, the first line term will all contribute to RQ. So let's first consider the contribution of this third term. So to see its contribution, we simply solve the following divergence equation. And we denote its solution by RQ plus 1 n. Thank you. Let me just draw. Okay, and this error is called Nash stress. All right, and now, so let's say you can solve this equation. Yeah, I probably won't go into the detail how to solve this equation, but here you somewhat just for the purpose of the heuristic estimate, you just consider this inverse divergence give the inverse of the derivative cost. Okay, and now, so if you take the C0 norm, from inverse divergence, since the frequency of the term inside of the inverse divergence has is localized at lambda q plus 1, you will get again 1 over lambda q plus 1 factor. I mean, if you want justification, you can perhaps use Bernstein. Okay, and then here we take C0 norm. Then you can write this way. Right. And as you see from our construction, so this was W, the size of AK is the RQ to the power 1/2. And here, this building block flow has the size, the C0 norm size 1. Right? So the bound of W is bounded by the RQ, C0 norm raised to power 1. And now you simply plug the inductive bound. Then what you get is the following, 1 over lambda q plus 1. And here you get delta, okay, let me write this one first, lambda q, delta q 1/2. And from here you get the delta q plus 1, 1/2. And you want to observe this term into the RQ plus 1, whose size is delta q plus 2. So perhaps what you want to show is this one is less than 1 over 10 of delta q plus 2. Okay. Then now is just a simple computation. Since lambda q is double exponential in q, lambda q plus 1, you can consider it as a lambda q to the power b. So if you divide this inequality by delta q plus 2, then what you need to show is the following, some constant times lambda q 1 minus b from here. And then here, okay, the delta q was lambda q to the power minus 2 beta. So you have 1/2 and then 1/2 b. And from here, you have b squared. And you want this one is less than 1 over 10. And to achieve this, all you need is just to show the exponent is less than 0. So if you do a bit more computation, the exponent is 1 minus b. And here, I think you will get beta 1 minus b and 1 plus 2b. And you want to show this is 0, less than 0. So, and then, okay, well, I think you can just see immediately. So this will be achieved if b is greater than 1 and beta is less than 1 over 2b. So now if I answer to Kajol's question, well, since you had, so again, this beta is related to the Holder exponent of our desired solution. Yes, so this beta corresponds to that Holder regularity. And then you want best beta. And then you just choose b close to 1, then you get almost 1/3. And here you can already see 1/3, the upper bound. Okay. Mm-hmm. So I only want to consider the contribution of this term to the new error, RQ plus 1. So I just denote the error generated from this term as RQ plus 1n. And our eventual error will be the summation of RQ plus 1n and some other error you will see. Question? Okay. If not, let me continue. So the next error that I want to consider is this oscillation error. Let me write it here. So this error is given as a solution to the following equation. And let me denote the error by RQ plus 1 oscillation. Okay. And as mentioned earlier, because of the construction of this perturbation W, this will actually have frequency localization. Like actually it's frequency localized at lambda Q. So it's enough to consider this term. And now let's just invert divergence and do the naive computation. So if you invert the divergence, this is what you're gonna get. Okay, you don't need RQ. And now you take the C0 norm. And then you get from inverse divergence again 1 over lambda Q plus 1. But notice that since we have divergence applies to this term whose frequency is localized lambda Q plus 1, if you just do direct computation, you will get lambda Q plus 1 cost, and then you will get W C0 norm square. So we had a gain from inverse divergence, but the gain is meaningless because of this divergence cost. And now if you remember the size of this C0 norm of W, this will be bounded by the size of RQ, C0 norm, which can't be smaller than the size of RQ plus 1. What we want to show is the opposite. So here we have an issue. Right. So to get around this issue, the idea is the following. So when you plug our ansatz into here, the problematic part is the building block flow because those are the part which has high frequency. And the idea is that we're gonna choose building block flow in a way that it solves the Euler equation, stationary Euler equation. You will see why the stationary solution to the Euler equation helps to deal with this more in detail in a minute. Okay? But before that, let me first talk about what are the candidates for this building block flow. So what we want for W so far is the following. So first, we want it to have high frequency. So more precisely, its frequency is localized at, let's say, around lambda Q plus 1. And now we require it to satisfy the stationary solution to the Euler. Okay. So there are a few candidates. The first one is the following, which is called Beltrami flow. This flow looks actually like this. Again, it has the shape of the plane waves. But the vector in front is chosen in a special way. In fact, the Beltrami flow is the eigen vector of the Kerr operator. And in particular, it satisfies the following equation. So it is a stationary solution to the Euler equation by putting pressure equal to this. Okay. So this is the first candidate. And the second candidate is the following, which is called Mikado flow, which is first introduced by Danari and Cyclohidi. See? And okay, so let me first start with the stationary flow, the standard Mikado flow. Just for the notation, let me denote it by the following. And then this looks like this. So here E3 is just a standard unit vector. And then it has the associate function psi E3, which depends on only x1 and x2 variable. So here the point of this associate function is that we choose it so that it satisfies the following condition. So the E3 directional derivative is equal to 0. And then you can easily check that it satisfies the following equation. This is all possible because of this condition. Okay, so it is again stationary solution to the Euler equation. And to achieve the frequency localization property, okay, but before that, sorry, let me first introduce the more generalized Mikado flow. So since the Euler equation is invariant under translation and rotation, you can actually apply the such motion to W, and then we introduce more generalized version of Mikado flow, which has the following shape. So in general, you have case direction, and then the associate function will only depend on the support direction variable. Okay. And now to have to achieve the first property, the frequency part, all we need to do is you simply rescale it by the factor lambda q plus 1, if this is the frequency that you want to achieve, and require or choose this associate function to satisfy the mean zero property. Well, now if you, okay, so let me just write the rescaled version as the WK, which is written as follows. Plus 1. And notice that this associate function is a periodic function with period lambda q plus 1 inverse. So if this one is mean 0, the next frequency will start from lambda q plus 1. Okay? So you can see that the minimum frequency of this one is lambda q plus 1. And also you can observe that the derivative cost of this function is merely lambda q plus 1. And by using that, you can also show that the frequency, when you take a projection operator whose frequency is much larger than this, it's all ignorably small. So in other words, the frequency of this is essentially localized at lambda q plus. Is it clear? Okay. You can just do computation. Yeah, so just, I think you need to choose, okay. I think you need to choose some AK vector. And then this one is some combination of the AK orthogonal to K. And this is combination of AK and the curl of AK. So you sort of use the 3D orthogonal direction. But this is clearer if you just plug these answers to the eigenvalue problem for the curl operator, then it's explicit. So this is eigen vector for the curl operator. Okay, I think it's okay. If I have some time remaining, I will just show you. It's just a simple calculation. Okay. Reference, okay, maybe Laszlo and Camilo's paper will also have description of Beltrami flow. Yes, and or just, okay, or just Maida's, okay, Maida's book, yeah. So if you look at the Maida's red book, that will be another reference for this. Yes, so 1/5 will definitely have. C01, yeah, that already have. Okay. Okay.
You fix the direction, x1. You just put a times sine x1 plus b times cosine x1, right? It's a 1. Just see a and b are vectors. And then just see what a and b is so that you can solution. It's a nice combination.
Right. Okay. All right. So far I've introduced the two candidates. One is Beltrami flow, and the another one is Mikado flow. And then let me compare these two. The Beltrami flow, actually, you have nice frequency support property because it's just given as this sine and cosine form, right? So you know exact frequency support, but the downside is that on the physical space, you don't have any support information. I mean, it actually occupies everywhere. It's just a sine and cosine. On the other hand, in the case of Mikado flow, you don't know exact information on frequency side, but you still know it's essentially localized at lambda q plus 1. But at the same time, if you look at the physical space, and if you choose this associate function to have, it's compactly supported in a small region, you have very nice information on the spatial support. Okay, so in some sense, Mikado flow, so you lose a bit of information on frequency, but you keep almost the same property, but you gain the spatial support. So actually, we're gonna use Mikado flow, we're gonna replace the building block flow by Mikado flow rather than the plane. Okay. Until where? This is the, was it there? Okay, okay. All right. Anything else? So now let me give a more detailed description of this benefit of Mikado flow. So let's just work with the standard Mikado flow. And So this is a periodic function on torus. So you just imagine some periodic box. And then so this is, let's say this is the E3 direction. And then you choose the associated function to be compactly supported in the following small region. Okay? And then the support of this Mikado flow will be given as follows. So it's supported in the following thin pipes. Okay? And now if you rescale it, okay, so if I just drop the bar, and then this will, the periodic box will have the side ranks lambda q plus 1 inverse. And so the size of pipe is also lambda q plus 1 inverse. And you will have a bunch of pipes, this periodic. But if you look at this box, it is supported nicely inside of this thin pipe. So why this is helpful? And now let's go back to our ansatz. So our ansatz has the following shape: the summation over k, the low frequency part times the building block flow. And now I replace this building block flow by Mikado flow. And now consider this W tensor W. Then, okay, since this WK, the building block flow has very nice support property. If you work, if you place each Mikado flow nicely, you can actually achieve the following condition. The support of WK and support of WK prime is empty when K and K prime is not equal. So there will be Mikado flow in multiple direction, but by placing carefully, you can let them have disjoint support. Okay. And now, if you look at the expression of W tensor W, by using this disjoint support property, there won't be any terms which involves K and K prime. The only term that you see is the self-interaction. Okay. Any question? Yes, plane wave. Yes, now I replace that by the Mikado flow, because that has again the spatial local, the frequency localization as in these plane waves, but it has nicer spatial support. And then, I mean, you can do the same computation as long as you choose the WK tensor WK. Its mean is equal to K tensor K. And this is achievable just by choosing this associate function to have a square mean, a unit square mean. Then by the same computation, you can show that AK again has the size RQ raised to the power 1. So now let's go back to the oscillation error. So oscillation error, let me just write down here, is again defined as a solution to the following equation. Okay. And then the left-hand side term, you just plug this into here. So this is same with, well, you can commute this two operator. So let me just write it this way. Divergence and AK square and WK tensor WK. Okay, and now you can see that. So previously the concern was the following: when divergence applies to this building block flow, since it has a frequency lambda q plus 1, we'll have the cost lambda q plus 1. So that's how the heuristic estimate was destroyed. But now you can see that when divergence is applied to this Mikado flow, since it's a stationary solution to the Euler equation, just see here. When divergence applied to here is 0. So divergence is only applies to AK, which is relatively low frequency. So this way you can save the heuristic estimate. Okay. What do I want? So this can be written as summation over K and AK square WK. Okay, so now let me do the estimate for this oscillation error. So this is given as the inverse divergence of the quantity that we just obtained. And then, so if you take the, again, C0 norm, and the bound, sorry, let me go up. And the bound will be, again, from the inverse divergence, you will get lambda q plus 1. But now, since derivative applies to the AK, you will have, and AK behaves like RQ, so you will only have lambda q cost. And then AK has the size, RQ raised to the power 1/2. So you will gain the size RQ, the RQ size, which was delta Q plus 1. And then again, this building block flow, if you take C0 norm, where is it? Here. So if you just take C0 norm, it corresponds to C0 norm of the associative function, which is simply bound. So it's a get unit scale. So now you want to show this is bounded by 1/10 delta Q plus 2. And again, if you do the same computation, this can be achieved if B is greater than 1 and beta is less than 1/B plus 1. Okay. Okay, now let me move on to the last error, which what's the numbering? 3, which is called a transport error. So in this error, we want to see the contribution of the following error term. And let me denote the error by RQ plus 1 T. Okay. Then you can again notice that we'll have the same problem because there is a derivative in front of the pattern, which will again destroy this heuristic computation. But to resolve this, the idea is somewhat similar. So to resolve this, we again replace the building block flow. Okay, let's say choose the building block flow to satisfy the following condition. When you apply this material derivative, it vanishes. Let me just try to stay close. Okay. So how to do this? To do this, let me first introduce so-called backward flow map, which is given as a solution to the following equation. Well, the transport equation that you just learned. Psi at t x0. So at initial time, at point x is x, and then it satisfies transport. Okay. And since this psi has a zero material derivative, if you consider the composition between the Mikado flow with this backward flow map, then their material derivative will vanish. So if you apply this to the composition between the building block flow and xi, this will be zero. So this will be our replacement. Okay, then you may ask, so what is this object? So let's see how it looks like. So first, note that this xi is the inverse of the forward flow map. Let's say phi. And what phi xt describes is the following. This corresponds to the position of a fluid particle, which start from a point x. So you start from a point x in time t. And this flow is governed by the vector field uq. Okay, so the position in time t is denoted by phi tx. And now, if you look at this composition, so their support, okay, maybe this is also a very simple exercise. Their support will be contained in the phi, and then support of the building block flow. And then you can see that, well, at initial time is same with x, so it's an identity. So it will be the same with the original Mikado flow, so in this composition. So at t equal to 0, it will be supported again in this thin pipe. But the particle in this thin pipe will move with a different speed, right? It will move with this velocity. So as time goes by, this pipe will be deformed. And also translate. Okay? But the good news is that as long as you proceed only the ellipsis time scale, so if this time scale is only up to the gradient of uq, L infinity inverse, then the pipe, the shape of the pipe remains almost same, and then it also doesn't destroy the frequencies. Okay, so what we actually do is that you start from the original Mikado flow and deform the ellipsis time scale amount, which will deform a bit, but this is still okay. And after that, so at this ellipsis time scale, you again go back to original Mikado flow and then deform, and then you just glue them by using the partition of unity in time. Okay? But then that partition of unity will have this ellipsis time scale, so that when you have the derivative, this material derivative, the cost will become this ellipsis norm. So that's why you had this ellipsis norm. Okay, but this is somewhat technical point, so it's okay. So here, anyway, the point that I want to raise is that, so to achieve this property, we just replace this building block flow by the one with the composition. But the thing is that actually, if you take the composition, you lose divergence-free condition. So to compensate it, you actually take the inverse of this deformation matrix. So then this will be still divergence-free. And the vector in front is the derivative of xi, and its frequency is same with the frequency of uq, which is lambda q. So this is actually harmless when you do the heuristic. Okay, so now if you write the ansatz, now it looks like this. It's more upgraded form, ak, and then the xi inverse, and then the composition between Mikado flow and the forward flow map, backward flow map. And then now if you take this material derivative, you can see that it only applies to this coefficient and the deformation. Times. Okay, so again, you no longer need to pay the lambda q plus 1 derivative cost. Okay, and for the computation of the transport stress error, I will just leave it as an exercise. And if you do it, you can see that the heuristic is essentially same with the Nash. Mm-hmm. This one? Yes? Uh-huh. But if you apply the divergence of this tensor product between this and itself, actually the divergence only applies to this eventually. So again, you don't need to pay the lambda q plus 1 cost. That's a good point, yeah. Thank you. Okay, so now let me give you summary. So eventually, our perturbation looks like this, AK, and then there will be some deformation matrix, and WK psi. And as I mentioned earlier, so this is divergence free. So we eventually want this omega is divergence free. So you actually need to add some divergence free correct. Divergence correct. Well, the idea behind is the following. So this is divergence free, so you can write it as a curl of some function. And then actually, the actual definition of W is the curl of this whole guy. Then this divergence corrector will correspond to when this curl applies to A. But when you write this way, you actually have gain here lambda q plus 1, the frequency of this one. And when the derivative hits AK, you only have lambda q cost. So this is sort of high order terms, so it doesn't destroy the heuristic. It's a side comment, but yeah, okay. So essentially, the correction looks like this. And with this form, you can achieve the C0 norm is bounded by delta Q plus 2 as you want it. Questions? So that's a good question. So like when you, okay, maybe let's just look at the oscillation error. Yes, so when you estimate this RQ plus, when you take this C0 norm of RQ, you actually need the C1 norm of RQ. So when you measure the C0 norm of RQ plus 1, you need gradient of RQ. So you need one derivative. So you always need one more derivative. So that's why you carry the, finite number of the derivative estimate. But eventually, if you use modification, you can actually close this loop. That's a bit technical. Sorry that I skip many technical part and just give a heuristic. Maybe it's Hof Camillo will give more details of it. Okay, but before we finish, I would like to say the following. So we also had a question on the Holder regularity of our eventual solution. So our eventual solution consists of the perturbation, consists of all the perturbation added up to the infinity. And now if you consider the size of the this perturbation, well, it's a C0 norm is bounded by delta Q plus 1, and its gradient is controlled by lambda Q, this is lambda Q 1/2 Q1. So by using interpolation, you can actually see that, let's say when you take C alpha norm, this is controlled by lambda Q to the power alpha delta Q 1/2. So you can see that this summation will be in C0 in time and Holder continuous in space as long as alpha is less than beta, which we know its bound is 2b plus 1 or p greater than. So this is a reason why we can go up to 1. Okay, do you have any question? Okay, so now let me move on to the C0 based Strong-Onsager. Okay. So the next section is, so again I will show heuristics, but this time for the Strong-Onsager conjecture. In C0 frame. So here, I only care about the non-conservation part. And the statement was the following: for any alpha less than 1/3, one can construct the weak solution in the Holder space with exponent alpha such that it satisfies the local kinetic energy inequality, but it has total kinetic energy. So here, now the challenge is we need to construct solution which also satisfies the local kinetic energy, local energy inequality. how B? Yes. 0? Yeah, this one, yes. Yes. No, just B can be anything very small, very close to 1. So, sorry, what do you mean by range? Yes, you can just choose B very close to 1. Yeah. Yes. So it's just so like okay. So the statement is the following: for any fixed alpha less than 1/3, you construct a solution, right? So this is inequality that you want to achieve. So your choice of beta should be greater than. So you will choose beta between alpha and 1/3, right? And then okay, and here if you okay, let's go. And so now it's beta is given, right, as a sum number between these two. And to achieve this, you just choose B sufficiently close to. Yes. So that's how actual logic goes. Okay. Okay, so strong Onsager conjecture. And the first thing that I'm gonna do is introducing the relaxed system. The relaxed, okay. Meaning that the equation for the approximate solution. And I gave you how to, I explained briefly about how to do this. You simply write your equation, your solution into two parts, the low frequency part and the high frequency part. You can also consider it like average part and some noise part. So this is high frequency, but assume that this frequency the frequency between these two has a separation. And then you write the equation for U bar. Then you will get the relaxed system. So the system is given as follows. So of course, it solves the Euler-Reynolds system. Because we are applying the same method. And then from local energy inequality, we obtain the following relaxed version. So this one was this one equal to 0 was the original inequality, but on the right-hand side, we have errors. Trace, 1/2 of the trace of RQ. So here I've introduced this new error, phi q. And indeed, if you write the equation for this U bar, then what you actually get here is that the divergence of minus 1/2 of the W squared W, and it's low frequency. And we denote this error. So this one, I just simply denote as the error phi q. And then as you will see later, it's similar to the Euler-Reynolds system, that you will correct this phi q by this cubic, the low frequency part of this cubic. Okay. So now the next step is solving the low frequency part equation. Okay. So since if you write W again as the correction, okay, so the perturbation between UQ plus 1 and UQ, then since this one has relatively larger frequency than UQ, you can decompose this equation for the W into low frequency part and high frequency part. And low frequency part can be simply written as follows. From the Euler-Reynolds system, you get the same thing. So divergence of the low frequency part of W tensor W plus RQ. And from the relaxed local energy inequality, you actually get the following. 1/2. So we now need to find a correction which solves the following system of. Yeah. So RQ is the matrix, and you just take trace. Yes, yes, yes. So yeah, if you again write this, so this, if you write this U as the average part, and this one is was like is given as the low frequency part here, and then there will be some term, then you can see that minus W square over 2 and mean, which corresponds to the trace of. So that's how you see this. Okay, so at a first glance, you think, okay, solving this seems to be quite hard because we just solved solving maybe this first equation was also non-trivial, and now we need to solve this system of equations. But there is a trick. If you now, let me again write it, the W in a following way. So the multiplication between low frequency part and high frequency part. Then you simply decompose into two parts. The first part will be used to correct the error RQ. And then the second part will be used to correct the error phi Q. And now, and again, this will be all Mikado flow, and you plug this into this equation. Then from the first equation, this is what you're gonna get. You have AR square, and then the mean of WR plus A phi square, the mean of W phi, plus RQ is equal to 0. The same as before. And then from the second equation, we have the following: 1/2 of the AR cubic. And then we apply again the cubic mean plus A phi cubic I think I missed 1/2, and then phi. And then recall that this the building block flows will be chosen again as Mikado flow. So you can write it as the following form. Let's say it's in the xi direction, that there will be some associate function in xi direction. And it's the same with the psi. Let's say it's xi prime direction, and associate function is xi prime direction. And now if you plug this into here, first you can see that so this cubic mean is the same with, okay, let me put it R. and this is for phi. So there will be a cubic mean of this associate function, and then 1/2 of the xi squared xi. But the observation is that since it's cubic mean, requires to be 0, right? And this way you can just drop this term from this. Then it's enough to solve the remaining term, which is not simple. So this is, in some sense, how to decoupling these two equations. So again, if I write down what I said, you choose the associate function for the Reynolds corrector to satisfy the cubic mean equal to 0 property. And then we just solve the remaining one. And as you've seen from the Euler equation case, since it's cubic, you first choose the cubic mean for the current corrector is equal to 1, then this will give the size of the coefficient as a phi as phi q raised to the power 1. Yes. Yes.
Typical something like this, you also make norm L2 norm usually equal to 1.
Yes, you will.
Choose like L3 norm equal to 1.
No, L2 norm is equal to 1, L3 norm is equal to 0. So there's no contradiction. You can still choose such function. Yes, but I will be there soon. Okay. So this is what you obtain when you solve this second equation. And now let's move on to the first equation. Then you can see that a phi is already determined. So now you treat this term together with RQ as a new error, and then solve as before. Okay. So previously you only have these two terms, but instead of solving, so you consider this as an error and then solve. Okay. Then for the optimal size of the current error, we require these two error are at the same size. So RQ actually has same size of a phi square and its mean. So this will again involve the square mean of associate function for the current corrector. Let's say xi prime phi cubic. And then the size of AR square will be determined by this size of RQ if we choose, as Kazuo just mentioned, the square mean of this associate function for this corrector is equal to 1. So actually, you should take summation over multiple vectors, but I just wanted to show the size, so I just ignored. Okay. So as I just briefly mentioned to Kazuo, this condition doesn't contradict to the cubic mean. So you can choose associate function which satisfy these two properties and also mean zero properties. Okay, and from here, well, as before, if you consider these two relationships, you can see that the size of AR is RQ raised to the power 1/2. And from here, since we are using the, this one should be square. Since we are using this homogeneous Mikado flow, so if you just plug the Mikado flow that I described before, you can see that their L2 norm and L3 norm and actually L infinity norm all have essentially same size. It's just determined by the norm of the associate function psi, and you're gonna choose that as a smooth function with the same scale. So this will be just size 1, and this will have size this phi q raised to power 2/3. So you will obtain another relation between the size of RQ and size of phi q. which is 2 sine.
It was very quick, and I understand but doesn't seem so like straightforward.
Mm-hmm.
You have to follow this path. So you started the global case with just this cosine.
Mm-hmm. Mm-hmm.
To see that when we have W that's with W,
Mm-hmm.
you get this low frequency term.
Sure, sure, sure.
Average of cosine squared.
Mm-hmm.
Now, if I look at this cubic term,
Mm-hmm.
with cosine, I get 0.
Mm-hmm. So that's not a good choice.
What?
So
I don't understand the role of this phi.
So if
And why do you even?
you mean
it's not so clear
phi,
because you get some average from W2.
but this I'm just talking about Mikado flows.
Right. So my question is like, okay, because you started, well, let's say cosine, then it doesn't work, and now we have these two options.
Then we.
So you're down one path.
And
you are trying to do something different, but you start at the end of the path.
Okay, so why I don't start from the plane waves?
Because then you wouldn't have this cubic term.
Yes. Yeah. So well.
It seems clear if you do this.
Sure.
You won't get into this issue. My question is why do you do this?
Because the reason I changed to Mikado flow was actually eventually we need to use intermittent Mikado flow. So this is actually later reason. But as you said, we can actually start from the plane waves. Actually, what when Iset proved this Stroman-Sagar conjecture for order space, he used plane waves. So still, that's possible.
So it doesn't have this cubic term?
Yeah. So like if you have cubic, then this satisfies the 0 property, as you said. So it satisfies this property. Yeah. So yes. But if you use Mikado flow, yeah, as you said, we need to choose associate function which satisfy these two. So it's a slightly more complicated. Yes.
Yeah, my question is like, this is one to transfer this expert term phi.
Yes. Yeah. So like here, the major concern is if you just try to solve this system of equation together, then it's more difficult. So I want to decouple these two equations so that to make the life easier.
No, I get that. But you want to solve that equation because you put a phi cube.
Yes.
Or substitution. Your relaxed system.
Yes.
I'm kind of questioning that.
Why we have phi q even at the.
Why do we have a phi q?
I mean.
If you didn't have a phi q, I could just.
No, I mean, so like in Iset's proof, there's still phi q. It's just a relaxed system. So even though you start from 0, if this one is what you want to achieve, is super.
I get that, but if you so this averaging is like if you have a quadratic term, which is really important to definite, averaging will not get you that. But it's a big term, it's not definite. So there is no apparent reason why you should have that in the relaxed system.
But like if you just consider one single flow, sure, what you said is correct. But in general, if you just consider this W, which has a simply high frequency, then their low frequency is non-zero. So yes. So yeah. No. I guess that helps understanding.
I mean, it doesn't.
But yeah. So this third one, the relaxed system, if you drop this, the divergence of phi q, then this is what you need to solve. All the right-hand side term is somewhat determined. And then the question is how gonna solve it when you write for the perturbation. To continue the iteration. Right. Okay, maybe we can continue. Okay, so where are we? So far I introduced the relationship between two. So since time's up, I won't go further. But next time, by using this relationship, I will show that in the Stroman-Saga conjecture in C0 framework, actually you will get the restriction of beta, which is bounded by 1/4 rather than 1/3. So this is a challenge that I mentioned in the last lecture. But so at the beginning of the next lecture, you will see where we get this restriction. And then I will explain how intermittency solves this restriction. Okay? Okay, let me stop here.